In order to set in motion a merry-go-round, you have to apply some force in the tangential direction. As you know, this force creates a torque that increases the angular speed of the merry-go-round. The harder and longer you push, the greater the increase in angular velocity. In the same way as the force changes the state of linear motion of an object, that is, its linear momentum, the torque changes its state of rotation. So, is there an analog to linear momentum for rotation? The answer is yes. We call it angular momentum. We know that the torque and the angular acceleration are related through the moment of inertia of the merry-go-round. Since the angular acceleration is the change in angular velocity with respect to time, we can express this relation in this way. And rearranging the equation, we obtain this expression here. We can compare this equation with the analog expression for the equivalent linear quantities. We know that the torque and the moment of inertia are the rotational equivalents to the force and mass, respectively, and that the linear equivalent to the angular velocity is the linear velocity. With this, we get this similar equation. Does something look familiar here? The first term in the equation is the linear impulse, and the second one is the change in linear momentum of the object. So, by doing this replacement, we have recovered the familiar relation between linear impulse and linear momentum. Based on this analogy, the second term of the initial equation, the product of the moment of inertia and the angular velocity, is called the angular momentum of the rotating body. Note that the angular momentum is a vector, and its direction will be the same as that of the angular velocity, that is, perpendicular to the plane of rotation. It will be pointing upward if the object is moving counterclockwise, and downward if it's moving clockwise. Because the product of the torque by the time interval is equal to the change in angular momentum of the body, the torque is the change of angular momentum over time. This means that if no torque is applied, the angular momentum must be conserved. Note that this is equivalent to Newton's first law. If there is no net force, then the object does not change its state of motion, and linear momentum is conserved. If there is conservation of angular momentum in a system, then the initial and final values of the angular momentum must be equal. Since the angular momentum is the product of the moment of inertia and the angular velocity, this implies that this product stays constant. Remember that the moment of inertia depends on the system's mass and how this mass is distributed, the distance in the case of a point particle, or the shape in the case of an extended body. Therefore, if we change the mass of the system, the radius in the case of a point mass, or the shape in the case of an extended body, we are changing the moment of inertia, and the angular velocity of the system will also change because the angular momentum has to stay the same. In the case of a point particle, this implies that the object will move faster when the radius is smallest. This is what happens, for example, with a planet orbiting the Sun. For the same reason, a skater will rotate faster when his arms and legs are closer to his rotation axis.